Hi, today we are presenting our work Asymptotic Cross-Entropy Weighting and Guided Loss in Supervised Hierarchical Setting using Tip Attention Networks. We are from Paris-Saclay University, MIT, the Mila Institute and the City of Montreal. Our thematic is the fine-grained classification, hierarchical classification and attention mechanisms. We deal with a dataset highly imbalanced and partially annotated. Domains involved are healthcare governance and especially here, biodiversity. Let's talk about insects. Insects are vital for environment, but they disappear at an alarming speed. 80% fewer insects in 25 years. And 1/3 of our food relies on insects. Insects demography assessment is limited by the difficulty to gather census data at sufficient scale. Our algorithms are in deployment on a butterfly crowdsourcing platform, a large-scale data collection of annotated butterflies pictures. Let's give some other numbers. It's the last ones. 90% of animals on Earth are insects. There are between 6 and 10 million different species, and merely 900,000 are identified currently nowadays. Merely 900,000 on 10 millions. That's an alarming number. There is thus a need for citizen science with socially beneficial application. Hence, enhancing fine-grained classification is required. We won for this proposition the IEEE award. Let's talk about our dataset. It's a highly imbalanced dataset, organized hierarchically. Each image at 3 levels: a family, a genus, and a species. A species belongs to one and only one genus, which also belongs to one and only one family. Hence, the distribution implies different levels of complexity for the classification task. We're able to learn very precisely the family label, much worse the genus and worse again the species. Hence, our work was towards enhancing the species classification as long as for the family we reach very rapidly 97-98% accuracy in top 3. You can visualize how each category is balanced here. Classes are highly imbalanced. Indeed, a balanced distribution represents linear cumulative distribution functions, while it is not the case here. The dot lines represented on those curves show how many classes contain more than a certain number of images. In this paper, we describe 2 methods. First, we are going to talk about hierarchical classification with the use of weighted cross-entropy and a penalization. In a second time, we will talk about attention mechanisms and the use of guided attention and a new loss that we introduce called guided attention loss. Let's talk about the hierarchical classification. So the idea, the gist of the idea is to classifying over families is simpler and more robust than classifying over species. For example, if the model is uncertain between 2 species A and B, which respectively belong to families 1 and 2, while being certain it belongs to family 1, it should predict species A. So the goal is to learning the underlying structure while preserving flat classification. We use a weighted cross-entropy WCE loss, which aims at penalizing parent-level classification errors. Here is the description of the loss. A divergence in 0 would imply small impact of the weighting, and a convergence to 0 in 1 would imply importance of the species. Hence, we decided to set experimentally lambda to 1, 1, 1. Lambda, which is lambda family, lambda genus, lambda species, for the choice of lambda parameter. Concerning the future work, we aim at implementing nested embeddings for hierarchical representation here. Then we dealt with the guided attention mechanisms. So you can see here on the schedule that we covered the hierarchical classification point. Let's talk about attention mechanisms and GradCamp. So GradCamp visualization tool use reverse gradient descent propagation. And we discovered experimentally that our CNN is likely to focus on the background. There is a bias. Let's take an example. On the left, we can see here that the insect is well concentrated by the network. There is no bias here. On the right picture, we see that the bias is merely focusing on the insect and more and mainly focusing on the background. Hence, we decided to use a mask or CNN segmentation as a prior. On the left, we can see a mask extracted, binary mask, and on the right, the result with a mask or CNN that we implemented in order to segment our butterflies. Even though the segmentation is generally correct, a few failure cases can deteriorate the classification's performance if used during test time. For this reason, we developed a method to leverage these masks during training through an additional loss, later called guided attention loss. The goal is that the features outside of the butterfly mask can be de-road since information is on the butterfly. Training modifications are less impacted by segmentation errors. Here is a description of our loss. For details, I need to switch to the next slide. In short, our loss could be described as this. It's the sum of attention mask multiplied by 1 minus segmentation mask on the sum of attention mask. Let's focus now on our accuracies. Using a ResNet 18, for example, we get in top 1 accuracy macro 81.29% using our guided loss on species, and in top 3 we get 92%, 93% using as well our guided loss on species. Concerning the families and genus, we yield very great results. 98% regarding the family accuracy and 92% regarding genus accuracy in top 1. For family and genus, it's only top 1 accuracy that are written here. A macro score is a per class average, whereas a macro score is a per sample average. We used for describing our work here a ResNet 18, but we yield slightly better results using a ResNet 50. Thank you very much for your attention.